Last time we looked at the exponential series after deriving the series for Euler's number E from its limit definition. We have obtained a series also for e power x, which is called the exponential function, and that series is called the exponential series. And then using Euler's formula, we have obtained expressions for cos x and sin x in terms of the exponential function. And then from there, we used the already known exponential series to get the series expansion of the cosine function. Okay. And then I asked you to find the series expansion for the sine function in a similar way. So have you done that? So you should get a very similar series. Okay. Here, if you observe cosine of x in this series, you have only even powers of x. Constant function, that one is a constant, that is also x to the power 0, right? So that's also an even power. X power 0 is also an even power of x, and this is x square, x power 4, x to the 6, and so on. So only even powers are there. Okay, and what will happen in the sine series? If you've done that, what did you get in the sine series? What kind of terms do you get? Yeah, you get only odd power terms. Okay, I hope everyone got this. You get only odd power terms in the series for sine x, the series expansion for sine x. So there, if you look at how we solved this, for, yeah, we have already done this. So sine x is e to the ix minus e to the minus ix divided by 2I. Okay. So here what we did is we wrote these two series expansions, e to the ix and e to the minus ix, and that's the same for sine. You don't need to change anything there. But instead of adding them, you should subtract this e to the minus ix series from the e to the ix series. So when you subtract, if you look at these terms, what happens? Here you will subtract the like terms. So 1 minus 1, that's 0. And on the other hand, here ix minus minus ix. So that is 2ix plus 2ix, right? Similarly, here minus x square minus of minus x square by 2 factorial. So they will cancel out because they're the same term. You're subtracting them, they will cancel out. And over here, the next is an odd power term. So what happens is in every odd power term, the same term occurs in both the series but with opposite signs. Whereas for even power terms, the same term occurs in both the series with the same sign. So when you subtract, all the even power terms will cancel out because they have the same sign and the same value. Whereas the odd power terms, when you subtract, they will add up because they have opposite signs. So a minus of minus a is plus a, like that. Ix minus minus ix plus 2ix, ix cube, well, minus ix cube minus plus ix cube, that is minus 2i x cube, and so on. So if you have done this properly, you would have got sine x is equal to, so remember, after subtracting, you will divide by 2i. Here you're dividing by 2i. So everywhere, after subtraction, everywhere you're getting a 2i term common. So that term goes away. And so what remains is this, x minus x cube by 3 factorial plus x to the 5 by 5 factorial, and so on. Only odd power terms. So if you compare these two, You can see the similarity and the difference. But here it starts from 1 and only even powers, and the denominator is always factorial of the same power, and the sign is alternating, minus, plus, minus, and so on. Right? Here also the sign alternates, but it starts with x, and every term has an odd power, and again the denominator is always the factorial of the power of that term, power of x in that term. So x cubed 3 factorial, x to the 5 5 factorial, and so on. Right? Sign is alternating. So both of these are alternating power series. Alternating meaning the signs alternate, and power series meaning every term is some constant multiplied by a power of x, an integer power of x. Okay. So let me just summarize these two. In fact, I'll start with the exponential series because that's also important. You should make a note of all of these. In one place so that you can quickly refer to them when we are doing later problems or developing more theory. Okay, this is exponential series, then the cosine series or the series expansion of cos x, that is cos x is equal to 1 minus x squared by 2 factorial plus x to the 4 by 4 factorial minus x to the 6 by 6 factorial, and so on. So you should write at least these three terms, to show the pattern. Okay, here also I'm writing more terms for you to see it clearly, but whenever you write the expansion, write at least three terms, the first three terms. Similarly, sin x has only odd power terms, x minus x cubed by 3 factorial plus x to the 5 by 5 factorial, x to the 7 by 7 factorial, and so on. Okay. All right. Now, you remember the properties of the cosine and sine function that we have mentioned before. Cosine is an even function, which means, what is an even function? If you have f of x is an even function, meaning f of minus x is equal to f of x. Similarly, f of x is odd if f of minus x is minus f of x. So we know that cos x is an even function and sin x is an odd function. That is very clearly seen from the series itself. Because what happens if you replace every x here? What is the use of the series? If you want to evaluate cos at some point, say approximately, so you know some standard values of cos. Cos 0 is 1, cos pi by 2 is 0, cos pi is minus 1, cos pi by 3 is root 3 by 2, sorry, 1 by 2, right? Yeah, cos pi by 3 is 1 by 2, and cos pi by 6 is root 3 by 2, and so on. But other than that, if you want to evaluate, say, cos of 1, there's not a standard value. But if you have the series, you can substitute that value, say 1, everywhere. So wherever, whatever value you're putting for this x, the same value has to be substituted here. So you get cos of 1 is 1 minus 1 by 2 factorial plus 1 by 4 factorial minus 1 by 6 factorial, and so on, and you will get an approximate value for that. Okay. So if you want to check whether cos x is an even function or see that it is an even function from the series, what you do is replace x by minus x. So if you replace x by minus x, here also everywhere x gets replaced by minus x. But what is minus x whole square? it is plus x square. So this sign will not change. Similarly, here it is x to the power 4 in the next term. There also, if you replace x by minus x, that doesn't change. So every term has an even power. So when you replace x by minus x, and this is an even number, right? This becomes plus x, well, becomes plus x to the power of the same number, right? The same number. So that power power obviously doesn't change. The sign also does not change, which means the series remains unchanged. So if you replace x by minus x in the cosine series, you get the same series, which is again equal to cos x. So that's why cos of minus x is equal to cos of plus x. But similarly, what happens if you replace x by minus x in the sine series? Here x is there, which becomes minus x. Here x cube is there, well, minus x cube is there, which will become minus of minus x cube. Minus x cube is minus of x cube. So minus minus plus. So just to write that, minus of x the whole cube is minus x cube. But here it is already one minus is there. So that minus will cancel with this new minus and become plus. So you will get terms like minus x plus x cube by 3 factorial minus x to the 5 by 5 factorial plus and so on. So every term has become the negative of what it was. So sine of minus x is equal to minus sine x. That's why it is an odd function. Okay, we could not see that clearly before, but from the series expansion, it is very clear that cos is an even function, sine is an odd function. What about e to the x? If you replace x by minus x, some of the terms, namely the odd power terms, will become opposite in sign, and the other terms, the even power terms, will remain as they are. So the resulting series is neither e power x nor minus of e power x. It is just e to the power of minus x series, which is a separate series. Okay, so e power x is neither even nor odd. Okay, this is just one use of the series expansion. What we are going to do is use these series expansions for evaluating certain limits. So again, we have seen polynomial or rational function limits where you have polynomial terms or polynomial divided by another polynomial. We have some methods for evaluating such limits. But again, suppose those functions are not polynomial. So for example, let us now evaluate this limit, which is a very well-known limit. Limit of sin x by x as x approaches 0. You might have studied this before. So can you tell me what is the value of this limit? Does anyone remember? Yeah, it's 1. This limit is 1. Okay. But again, we cannot use L'Hopital rule for this because we don't know differentiation yet, and limits come before differentiation. So that's really not sensible to do, right? We still have to do differentiation later. And in fact, finding the derivative of sin x involves evaluating this limit. So it will be somewhat circular if you use differentiation to find this limit for those who have studied L'Hopital rule already. Okay, so we have to evaluate it some other way. But if you know the series of sin x, this is not difficult to do. Firstly, can you get the value by direct substitution? If you substitute 0, the denominator, yeah, you cannot get it because sine of 0 is 0 and x, right, the numerator becomes 0 and the denominator also becomes 0. Sine 0 is 0 and x is just 0. So this is a limit, or this is rather an indeterminate form, right? Indeterminate form of the form 0 upon 0. So this is one where you cannot do it by just substitution, you have to apply some techniques. But unlike before, we cannot now say that x is a root of the polynomial or something like that, because sine x is not a polynomial. It's a so-called transcendental function. It's not a polynomial. So we cannot use long division here or factorization. So what we can use is this series. Then it will be almost like what we did before. Because as you can see, although it is not a polynomial, it is like a polynomial. It has terms which are all powers of x. It's not a polynomial because it has infinitely many terms, whereas a polynomial by definition has finitely many terms. That is the only difference. But otherwise, for all purposes of evaluating the limit, it behaves like a polynomial in the sense that it has these x terms common. So we can cancel this x from every term when you divide by x, and you can get a new series. So let's do that. So I'll say that this is equal to, so this x in the denominator I'll write first as 1 by x, because I have to write a series here. Okay, so this series will be the sine series. Okay, so the sine series from where we have derived it here, the sine series is x minus x cube upon 3 factorial plus x to the 5 upon 5 factorial, etc. Okay, 3 terms is sufficient. So I still cannot substitute, because if I do, then I'll get a 0 in the denominator. But now observe that every term has x common and there is an x in the denominator. So we can cancel one x from every term to get 1 minus x square by 3 factorial. The denominator is not changing. 3 factorial does not become 2 factorial. Okay, it remains as it is. Then x to the 4 by 5 factorial, and so on. Next will be x to the 6 by 7 factorial if you look at this term. We are not writing it. Now can you substitute? Can you put x equal to 0 now? There is no x in the denominator anywhere. So if you do put x equal to 0, this is 1. It's constant. So that doesn't change. That will remain 1. Whereas the second term has an x in it. So x to the x square, where x is 0, is 0. X to the 4, when x is 0, that's also 0. Every term after this has some power of x, some higher power of x in it. So when you put x equal to 0, all of those become 0, leaving only the first term, the constant term. So that's why this limit is equal to 1. Is it clear to everyone, or should I repeat any part of this? We are going to use the cos series similarly somewhere else. So for some other limits, we'll use cos series. So there's no question of evaluating. Sorry, the second equation is cos. This one, this one is cos series. Third one is sine. I have not used it yet. I have only derived it. Okay. Oh, you're saying this one? No, this is not. In this problem, this is not cos series, because as I said, the denominator is not changing. The denominators are 3 factorial. So if you compare, here you have 2 factorial. Here you have 3 factorial. How did I get this series? We have sine x by x. So I'm writing this. One second. This x in the denominator is this 1 by x, and this sine x is this entire series. Okay. Now cancelling this x everywhere. So the powers get cancelled, right? This becomes 1, this becomes x cube becomes x square, x to the 5 becomes x to the 4, and so on, just cancelling the x in the denominator. So that's how we get this, the next term. Okay, it is not the cosine series. Fine. Okay, so now we'll use the cosine series for evaluating a similar limit. But first of all, if I ask for the limit of, let me write it. Suppose I similarly ask limit x approaches 0 of cos x by x. Do you need the series expansion for evaluating this? Remember, whenever you have to evaluate a limit, first of all you should substitute and check whether there is any problem. If you can get it immediately from the substitution, nothing else needs to be done. So here when you put x equal to 0, denominator again becomes 0. Denominator becomes 0, but the numerator becomes cos of 0. What is cos of 0? 1, right? So this is 1 by 0, that is infinity. Okay, so there is nothing indeterminate about this limit. The limit is infinity. Okay, we don't actually write 1 by 0, but it is infinity. So I can directly write, no, we won't take the series because the first or the best method for evaluating a limit is substituting it. Only if we get an indeterminate form. Which are the indeterminate forms? 0 upon 0, then 1 to the power infinity, or infinity upon infinity. Similarly, infinity minus infinity. We won't encounter all of these forms, but these are the indeterminate forms. In these cases, we cannot get the value directly. Yeah, even if we take the series, we get the same. That's correct. Even if we take the series, if you look at this, you have starting with 1, right? Here in the sine series, the first term is x, and every term has x in it, like at least 1 power of x in it. In the cos x series, only the first term is constant, and only the remaining terms have higher powers of x, positive powers of x. So when you divide by x, this will remain 1 by x. Every term from the second one onwards will have some x remaining even after division, but the first term will be 1 by x. So that's still infinity. As x approaches 0, 1 by x approaches infinity. All the other terms become 0, but because of the first term, you get infinity. But anyway, even without taking the series, you can say immediately from the indeterminate form, from the substitution, that it is not an indeterminate form. 1 by 0 is infinity, or non-zero by 0 is infinity for limit, for finding limits. Okay, so yeah, we could look at let's say 1 minus cos x divided by x square. Okay, so now for this limit, you cannot get the answer just by substitution, because let's see what happens to the denominator when you put x equal to 0. X square is also 0, no problem. What about the numerator? 1 minus cos of 0, but 1 minus cos of 0, 1 minus 1, that is also 0. So this is an indeterminate form, which means you have to use some other methods for evaluating it. And again, we have the series, the cosine series, so we'll just use that. Okay. So similar to what we did here, you have 1 by x sine x here. Here you have 1 by x square times 1 minus cos x. So we'll write 1 by x square 1 minus cos x. Now cos x is given by a series expansion. So that series expansion I will write here. So this cos x will become this series 1 minus x square by 2 factorial plus x to the 4 by 4 factorial. I'll write one more term here because the first term is going to get cancelled. Okay, this is it clear to everyone that this 1 minus cos x by x square can be written in this way? Or should I explain this step? See, the 1 by x square is over here. This first one is over here. And minus cos x has become minus of this series. Now, we can't cancel the x square first because this x square cannot be cancelled yet because this 1 is there. But here if you observe, the first term of the series is 1 and we are subtracting the series from 1. So this becomes 1 minus 1, that gets cancelled and becomes 0. Then we have minus of minus x square by 2 factorial, that is plus x square by 2 factorial. Similarly, minus of plus x4 by 4 factorial, that is minus x to the 4 by 4 factorial. Similarly, next would be minus of minus plus x to the 6 by 6 factorial and so on. Now x square is common to all the terms, right? Here you have x square in the denominator, here you have x square, here it is x to the 4 which is x square times x square, then x to the 6 which is x square times x to the 4 and so on. So when you cancel this x square, this gets cancelled, this becomes x square, this becomes x to the 4 and so on. So here you will get, I'm sorry, I forgot to write this limit everywhere. Actually you have to write it. Okay. So this limit is there everywhere. Right. So this becomes limit x to the 0 1 by 2 factorial minus x square by 4 factorial plus x to the 4 by 6 factorial and so on. Again, note the denominators are not changing. You're only cancelling the powers of x. So we're subtracting 2 from all the powers of x because you cancelled x square. Denominators remain as they are. So again, when you substitute x equal to 0, the first term is constant, second term, third term, all the other terms have x in them. So they all become 0. So the final answer is 1 by 2. Right, only the first term 1 by 2 factorial and 2 factorial is 2. So this limit is equal to 1 by 2. I hope that's clear. Is it understood? Do you want me to explain anything here? Okay. All right. Similarly, I'll mention a few more limits that can be evaluated in the same way. So e to the x minus e to the minus x by x. Okay. This looks similar to the sine definition, but note that I is not there. It is not e to the ix and e to the minus ix. It's just e to the x, e to the minus x. So it's actually there is a function called the hyperbolic sine function. Okay, it's okay if you don't remember these definitions. I'm just showing you the definition, but you don't need to remember them. So this is called hyperbolic sine function, which looks very similar to the sine function, only that the exponents are just x and minus x, not I and minus I. And here there's no 2i. We change the sign of what? What are you asking? Are you asking about this one and huh? No. It's not just a change. Well, it is similar. It's almost a change of sign, but you have to look at it carefully. So what you do is write the series for e to the x and the series for e to the minus x, both, and then see what cancels out. So some of the terms will cancel out. See what cancels out and what remains, and then in the remaining series, whatever terms are there, divide them by x. Okay. As you can see, this is also an indeterminate form because as x approaches 0, the denominator is clearly 0, but the numerator is 1 minus 1, right? Because e to the x and e to the minus x both become e to the 0, which is 1. So here you get again 0 by 0. So definitely you cannot just evaluate it by substitution. You have to use the series for e power x as well as the series for e power minus x. Not the sine series, not that. It's not just a sign change. It looks like that. Final answer looks like that. So you have to change the signs of only some terms, but um, if you just do that, there's no justification for it. You have to prove that that's true. So it's better that you take e to the x and e to the minus x and then obtain the series from that. Okay. Because the hyperbolic sine function is very similar to the sine function. Yes, Sanket, you can ask a question. Yeah. Sanket, do you have a question or you're not able to? Okay, wait. I think now you should be able to hear me. Okay. Right. Okay. Fine. Then this is one such limit.
Aditya.
Sanket, do you have any question? Okay. Then slightly more complicated one. The answer is e to the x, e to the minus x. Yeah, the answer is 2. Yeah, you should be able to figure that out, but the answer is 2. Let's see. How about this? I'll do actually. How about sine ax by x? I'll do this problem. I'll write one more problem as a homework. Okay, which is similar. Take I think there is a, yeah, that should be good. So both of these are 0 by 0, right? So sine x by x, obviously. What about this one? Here you have again denominator is clearly 0, and the numerator is e to the 0, that's 1, minus 2 into 0, that's 0. So 1 minus 0 minus 1, that's also 0. Right? So this is also an indeterminate form. We'll have to evaluate this by using the series expansion. So this is very similar to what we did before, but little more complicated. So you can try this later. The sine x by x is also an important limit. We'll solve this now. You can do the other problems later. Fourth one you can do later because that's similar. Numerator for this one. Fourth one, yeah, because it is e to the 0 minus e to the minus of 0, right? So, but this is 1 minus 1. Because you're putting x equal to 0 in the entire expression. Yeah. Okay. So all of these are indeterminate of the same form, 0 by 0 form. Answer for the fourth one is 2. No, you get the answer only by using the series expansion and then cancelling. So similar to what we did before. It's indeterminate form. To evaluate the limit, you will get the answer is 2. Okay. Okay, so the this one, there are two ways of doing this. One way is easier, but one way is easier, but it uses the answer that we already got. Okay, it's easier to do, but the thinking required is a little complicated. Well, not really, but different from what we've been doing. Okay. It doesn't. Can you stop using the annotation, please? So if you use a series expansion here, that will be also helpful for the next problem, sixth problem. So we'll first do it by series expansion, and then I'll show you the other method. So if you are doing series expansion, yeah, the answer should be A. Okay. If you use series expansion, here you have 1 by x, then sine ax. But how do we get this series for sine ax? We know that the sine series is this. Sin x is x minus x cubed by 3 factorial plus x to the 5 by 5 factorial, etc. But what about sin ax? Remember that the name of the variable does not matter. So this x can be replaced by anything, like we did before for minus x, or particular values like 0, pi by 2, and so on. This x can be replaced by anything at all, including ax. So if you replace x by ax in this series, here you will get ax, whereas the next term is a cube x cube by 3 factorial, then a to the 5 x to the 5 by 5 factorial, because it's what, ax cube ax to the 5, right, and so on, right? So this, again, x is common to all the terms, so it can be cancelled. You're left with a constant, right, minus a cube x square by 3 factorial. Remember, a, even a is common, but anyway a is not in the denominator, so a remains as it is. A's power does not decrease because we are not cancelling it with anything. So this is a cube x square, and then a to the 5 x to the 4, and so on. Now it is possible to substitute x equal to 0 everywhere, which leaves the first term, the constant term a, as it is, and makes all the remaining terms 0. So the answer is A. Something similar you'll have to do for the sixth problem, where you have e to the 2x. You know the series for e power x, but remember that x can be replaced by anything, including 2x. You'll have to do the series expansion there accordingly. Now the other method of evaluating this is a, let's say, a cleverer method, but it relies on already knowing the limit. It's a method of reducing the limit, the new one, to the known one. So what we have is sine ax by x. What we know is that limit x approaches 0, sine x by x is 1. Here, this is ax, but this is just x. So it is not exactly in this, form, because here it is x in both places, right? So to make it the same, you can multiply and divide by a. So you make x into ax by multiplying on a in the numerator, so that the value is the same. You're not changed anything essentially, right? The value is the same because you multiplied by a and divided by a as well. But now this a is a constant, which means you can even write, and it's a non-zero constant. That's important. Okay. So you can write it outside the limit and write this as ax approaches 0, sine ax by ax. Now it is almost similar, except that here also it should be x. But as x approaches 0, ax also approaches 0. So this is also the same. So now this new limit is exactly like this, only that instead of x it is ax everywhere, but that doesn't matter. It's the same as calling this a times limit y tends to 0 sine y divided by y, isn't it? It now it is exactly in the same form where y is ax, right? If you replace ax by y, this and this are the same, only the name of the variable is different, but the name doesn't matter when you're finding the limit anyway. So this is exactly the same. So we know that this is equal to 1. The whole thing is multiplied by a. So the final answer is a. Okay. I hope you understood this method, but you have to be careful if you're using it. Okay. In the sixth problem, you cannot do this because it's not like any known limit anyway. It's not just a matter of x being interchanged with 2x, right? X being replaced by 2x. The sixth problem, it is e to the 2x minus 2x minus 1. We have not evaluated anything exactly like that before. So you have to use series expansion there. But this is a special case. Any questions about this? Fourth sum, I already told you, e to the x. So we know the series for e to the x, right? And if you want the series for e to the minus x, all you do is replace x by minus x. So e to the minus x is 1 minus x by 1 factorial plus minus x square by 2 factorial plus minus x cube by 3 factorial and so on. Oh yeah, sure, sure. So the class is over. You can, if you have another class now, you can leave. Okay. So yeah, this is it. You just have to use this series. Thank you. I will send the notes. Yes.